All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. And today, what I'm going to be working through, ladies and gentlemen, is working out several more examples of looking at how to balance redox reactions, because I know it's a skill that's relatively new to you guys. And I did give you guys some sample problems to work at the end of the PowerPoint, and I thought it'd be good to put a video out that walks you through step by step of how you'd be able to get to the answer. Now, for those of you, some of you might want to just kind of skip ahead and see what are the answers. And so feel free to do that. Feel free to find those spots. And, I'll try to help you out there as best you can. You can check that. And if you get stuck, then maybe you need to watch the video. If not, then, you're good to go. You'll be able to check yourself and go from there. So, let me go ahead and dive in here with the first example, or the first problem that I gave you guys to work on individually, which had to do with the following reaction, right? So in the PowerPoint, we talked about the reaction of SN2+ ions plus 2 Fe3+ ions going to, we've got the 1,10,4 ion plus we've got 2 Fe2+ ions, right? And so remember that when we're talking about balancing redox reactions, remember we have to make sure that we balance the charge and the number of substances that are present, right? And so it seems that we've got that taken care of, at least from this expression. The other thing that we're going to have to want to consider and make sure is taken care of is what are our oxidation numbers, because we need to identify what's been oxidized and what's been reduced. And so now kind of for this particular problem, the nice thing is we've got nothing but ions. And if you remember, the charges on ions are the oxidation states for each of our substances. And so I'm actually going to write this in a different color just so that we can keep it kind of different here, right? So for 10,2+ ion, it's going to have an oxidation state of +2. For each of our iron 3+ ions, they have an oxidation state of +3. 10,4 has an oxidation state, 10,4 ion has an oxidation state of +4. And iron 2+ ions have an oxidation state of +2. All right, so now we see those oxidation states. Obviously, we see the changes that are occurring in each of those substances. And looking at that, we should be able to identify that the substance that's being oxidized is the SN2+. Remember, oxidation is loss of electrons. So SN2+ AQ is being converted into SN4+ AQ. And then our half reaction, or the thing that's showing us what's being reduced, that would be our iron ion, our iron 3 ion. So we've got the 2 Fe3+ AQ going to 2 Fe2+ ions. Okay. Now, in terms of balancing a redox reaction, I'm going to be honest, this one's a really simple one because we only have those individual ions. We have no oxygens or hydrogens to deal with. And so we look at it, we've got the same number of atoms on both sides. And so in terms of balancing this one, the only thing we need to make sure is going on is, do we have the appropriate number of electrons for each substance, right? And so for the 10,2+ ion going to 10,4+ ion through oxidation, because it's the oxidized reaction, we know that the electrons need to be on the product side. So we've got, all right, it went from 10,2+ to 10,4+. So that means that 10,2+ lost 2 additional electrons. That's what's going to make this to where the sides or the charges are equal, right? This is a 2+ charge over here. Adding those 2 electrons makes a 2+ charge over here. All right. And so we've got that. And then we look at our reduction reaction. This is where electrons are gained. So that means the iron 3+ ions are gaining electrons. Currently, there's a +6 charge on the left. There's currently a +4 charge on the right. So in order for those to balance out, we're just going to need to add 2 electrons as well. And man, this one works out really nicely, right? So if we were to combine everything, we see that the 2 electrons would be canceling out, combine them, so our balanced redox reaction is actually the same reaction that we started with. So we had SN 2 plus AQ plus 2 Fe 3 plus AQ produces SN 4 plus AQ plus 2 Fe 2 plus AQ. All right. So in terms of a balanced redox reaction, that one was actually pretty simple. Nothing too crazy had to happen there from this particular reaction. So hopefully you're feeling pretty good about that one. So this would be your final answer for the balanced redox reaction, right? Now let's take a look at the next one. I can promise you the next one is a lot more involved. So the next reaction, they told us it was in acidic solution, but it's the permanganate ion. So we've got MnO4 minus AQ plus the oxalate ion. So we got C2O4 2 minus AQ produces, we end up with Mn2 plus, so the manganese 2 ion plus, we end up with carbon dioxide that is aqueous. So carbon dioxide that has been dissolved in the solution. Okay. And actually, I think it's actually telling us that it's actually supposed to get bubbles. So it shouldn't be dissolved. There should be some of this bubbling out. So we'll just change that real quick. Should be carbon dioxide as a gas. Okay. Now, just like with our previous example, we're going to need to have everything balanced and everything, but we're also going to need to kind of split everything up this time into our oxidation and reduction half reactions. Well, in order to do that, we need to first identify what's been oxidized, what's been reduced, and to do that, we're going to need to assign oxidation numbers. Now, for me personally, I like working with things that are kind of the simplest to work with. So like I see automatically over here on the product side, I've got a monatomic ion. So that means that the manganese 2 ion has an oxidation state or an oxidation number of +2. All right. Then we can start dealing with kind of other things. Let's just stick with the product side. I like that we've got oxygen over here. It's paired up with carbon, so we go back to our rules and we know that oxygen is going to have a -2 oxidation state in this particular case. There are 2 of them, so that means that the carbon is going to have an oxidation state of +4. Okay. Now, looking at what we're dealing with on the reactant side, I've got oxygens again, so each oxygen in this case has that -2 oxidation state, which doesn't change all that much. Now, interestingly enough, we've got manganese that's paired up with oxygen, so that's if we're trying to figure out what it is, we've got a total of -8 due to the oxygen because we've got 4 of them. And in order for this to have an overall minus charge, that means that the oxidation state for the manganese is +7, right? Because you got 1 manganese that's a +7 oxidation state. You got 4 oxygens at -2. 7 minus 8 would give us -1. which matches up with the charge for the permanganate ion. Okay, and then if we look at our oxalate ion, we've got, again, same scenario. We've got 2 carbons that we don't know the charge of. We've got -8 for our oxygens, has to equal -2. If I just solve that algebraically, I got 2x equals 6, so x equals 3. So each carbon in the oxalate anion has a +3 oxidation state. All right, so hopefully that makes sense. I'm going to erase that because I'm going to need that space. But feel free to pause the video should you need it going forward. Okay, so from there, now that I've assigned all my oxidation states, I can then move into the next task of splitting this up into what's been oxidized and what's been reduced. Okay, now remember, in terms of what's oxidized, that's the substance that's losing electrons. And from this particular reaction, what we see as being oxidized would be the oxalate. The carbon within oxalate is what's been oxidized because it went to +3 to +4. So we got C2O4 2 minus AQ. It's going to go over to CO2 as a gas. Okay, so that's our oxidized portion of our reaction. And then our reduction portion of the reaction is going to be the permanganate ion. We notice that the manganese went from +7 to +2, so we see that it gained electrons. So we've got MnO4 minus AQ. I'm going to try to leave some space here. Well, we'll hold off on that. It's going to make Mn2 plus AQ, right? And so, at least from this particular perspective, we have now separated this into 2 separate reactions. We've got our oxidation half reaction, and we've got our reduction half reaction. Okay. And so for the sake of trying to keep things consistent here, let's just focus on balancing first the oxidation half reaction. So I'm going to erase the bottom, but don't worry, we'll revisit that here shortly. So we erase the reduction half reaction. We'll come back to it. So now we want to balance the oxidized half reaction. Well, so I'm looking at this. Remember, the rules state, all right, you want to balance your atoms first, and you want to balance things other than oxygen and hydrogen first. So I'm looking, and it appears that there are 2 carbons on the reactant side. There's only 1 on the product side. So what I need to do is I need to add in a coefficient of 2 in front of my carbon dioxide. All right. Now, so we do that, and that gives us 2 carbons on each side. That's good. And then all of a sudden we look at it and we're saying, okay, how many oxygens do we have? Well, we got 4 oxygens on the reactant side. We now have 4 oxygens on the product side. That's a good thing. So now we've got our atoms balanced. And so we don't need any hydrogens or anything. So then we just need to figure out, okay, well, how many electrons were lost? Okay, and so looking at that, we look at the overall charge on the left. It's at -2 currently, and it's neutral on the right since oxidation is loss of electrons. We're going to come over here and we're going to say, all right, I know that there were 2 electrons that need to be added over here that are lost so that each of those carbons can go from a +3 to a +4 oxidation state. Okay, and looking at that, at least for now, that takes care of our our oxidation half reaction. That's all we can do at this point. Which, looking at that, I'm feeling pretty good about that. So let's rewrite our reduction half reaction. Maybe I didn't need to erase it after all. Silly Mr. Kenton. All right, so you got MnO4 minus AQ is going to go to Mn2 plus AQ. All right. Well, if you remember your steps, the steps tell us that we want to balance out the number of atoms on each side first by looking at things that aren't oxygen and hydrogen. When we look at our manganeses, we have the same number of manganeses on both sides. Okay. And so looking at that, like, okay, manganese is balanced, but then we look on the reactant side and we got those 4 oxygens that are present. Now, in order to balance out the oxygens, remember we want to add waters to the side where there's no oxygen. So in order to balance this out, to get 4 oxygens, we need 4 water molecules. So we got 4 H2O liquid. All right. And so now we look at that. We've got 4 oxygens on the product side. We've got 4 oxygens on the reactant side. Now, in doing that, we just introduced hydrogens. This is where the fact that this reaction is an acidic solution is going to come into play. We know that in order to balance out the hydrogens, we're just going to add an appropriate number of H plus ions to the opposite side. And so that's going to change this to MnO4 minus plus, I'm actually going to go ahead and kind of clean this up a little bit because I'm going to need a little bit more space. We've got MnO4 minus AQ plus 8 H plus ions, right? And so when we look at that now, we've got 1 manganese, we got 4 oxygens, we have 8 hydrogens. So now from a mass perspective, we've got the same number of atoms on both sides of our equation. Now the next piece is going to be, all right, so manganese was reduced. How many electrons do we need to introduce in order to balance that out? Well, if we look at it, or if we look at the overall charge currently, on the reactant side, the charge is plus 7, because you got the 1 permanganate and the 8 hydrogens, so that's plus 7. And then on the product side, you have a plus 2 charge, or a total of 2 plus charge. And so in order to balance that out, that means we're going to need to introduce 5 electrons on the reactant side. Now, it should make sense. We want the electrons to be on the reactant side because this is a reduction reaction. Manganese is going to gain those 5 electrons, and it's going to be converted into that manganese 2 plus ion. All right. And so when we look at it from that perspective, our reduction half reaction has now been balanced. Okay. And so we've got our oxidized half reaction, which is balanced. We've got our reduction half reaction that's now been balanced. So now the only thing we need to do is make sure that the number of electrons is equal, right? Because we currently have 2 and 5 respectively. So the common factor between each of those is going to be 10. So we're going to need to multiply each of those equations by some factor to get to 10. So for the top one, we're going to need to multiply it by 5. And then for the bottom one, we're going to need to multiply it by 2. Okay. And so then what we would have, if I rewrite everything, so our oxidized half reaction would then become, and I'm actually going to combine 2 steps here if you guys are okay with that. I'm going to go ahead and combine everything into one whole reaction by adding the reactants and products together. So I'm going to have 5 C2O4 2 minus AQ plus, on my reactant side, I'm going to have 2 MnO4 minus AQ plus 16 H plus AQ plus 10 electrons produces, I'm going to have 10 carbon dioxides plus 2 Mn2 plus ions plus 8 liquid waters plus 10 electrons, right? Whew, a lot of stuff that we're dealing with now. All right, and so then, as you can see, we've combined both of those equations. And so now I can begin to cancel out things that are showing up on both sides of the equation. Now for us, that's the 10 electrons that are here and here. And so when we look at this, our final overall balanced equation for this process in acidic solution would be 5C2O42 minus AQ plus 2MnO4 minus AQ plus 16 H plus ions AQ produces 10 carbon dioxide molecules plus 2 manganese 2 ions plus 8 waters. Okay, and that would be our balanced equation if this were in acidic solution. Okay, it's a lot of work that we had to do just to be able to go through that and to do this, right? So this was in acidic solution. This was in acidic solution. Now, I know in the PowerPoint that I asked you guys to look at the same exact reaction and asked you guys to take a look at it if it were in basic solution. Now, remember, the steps to go from, if you're doing acidic versus basic, they're exactly the same, except your ending step, right? So if you think about it, when we went from multiplying everything and we had this giant equation that's listed kind of second from the bottom, this one right here, right? We stopped there because we had got our electrons balanced. The only difference would be if we were to go through and do this and we wanted to do it in basic solution, it would change in this last step. So if you guys are okay with it, I'm going to erase some things. And I'm just going to bring this equation that I got the arrow pointing towards, I'm going to bring it up to the top, and I'm going to go through and I'm going to balance it as if it were basic. Okay, so kind of bear with me here for a second as I get it erased. You guys are probably thinking to yourselves, Mr. Kenton, this is torture. Why would someone want or need to be able to do this? Well, that's a good question. It's not all that torturous. I find it kind of therapeutic. There's just something really refreshing or encouraging about being able to go through a long problem and to get it all figured out. So what we're doing is we're dealing with this now as if this same equation were basic. Like I said, you can follow me getting up to the point that I'm about to redraw earlier in the video. But now I'm just going to be dealing with that last step of what do we do if it's in basic solution. And so let's rewrite kind of our combined reaction. We have, it should be 5C2O4 2 minus AQ plus 2MnO4 minus AQ plus, and I believe it was 16H plus. We had 10 electrons, and then that's going to go to 5 CO2s, 2 Mn2 pluses, we had 8 waters, and we had 10 electrons. Sorry, I couldn't get it all fit into one line. Now, if this is in basic solution, remember what we have to do is we're going to have to add an appropriate number of hydroxides to the side that contains the hydrogens, because if it's in basic solution, it's not going to have excess H+, it's going to have excess OH-. That should be there. And so what that means is we're going to need to neutralize these 16 H+. Now, because it's in basic solution, that means we're going to need to add hydroxide to both sides of our redox reaction, okay? And so when we do that, if we rewrite this, you would get something that looks like this. So if I add all that together, we're going to have 5, let's see if I can fit this all on here, C2O4 2 minus AQ plus 2 MnO4 minus AQ plus 16 H plus AQ. To balance out those hydrogens, we're going to add plus 16 OH minuses plus 10 electrons is going to produce, oh boy, didn't leave myself more room, did I? I've got 5 CO2s as a gas plus 2 Mn2 plus AQ plus 8 waters plus 10 electrons plus, now we added 16 hydroxides to the left, we got to do the same thing on the right, so plus 16 OH minus AQ. Now, what that's going to do is this is going to combine these terms right here to give us 16 waters, right? And so now, as we go through and we're starting to cancel things out, what we're going to see is, all right, the 10 electrons are going to cancel, but we're also going to see that there's going to be a change in the waters. So over here we have 8 waters on the product side, but now we have 16 on the reactant side. So the 8 waters are going to cancel, and this is going to get simplified to simply 8. So then in basic solution, if I now rewrite this, my basic solution balanced redox reaction is going to be 5 C2O4 2 minus AQ plus 2 MnO4 minus AQ plus 8 waters produces 5 carbon dioxides plus 2 Mn2 pluses plus 16 hydroxide ions. Okay. And so this would represent the balanced equation if this were in basic solution. Okay. Whew. So now you can check yourself. Did you get those 3 right? I hope you did. If not, feel free to look back over this video. It walks you through it step by step. Hopefully it's insightful. Hopefully it's helpful. If you do have any other questions, please don't hesitate to ask, ladies and gentlemen. That's what I'm here for. Hope you find this useful, and I look forward to seeing you guys again soon. Take care.